Hello. So today is the week 11, I suppose, and we'll be going to the previous year questions only and the tutorial. So in tutorial, we'll be implementing the Wiener filter, same as that sir did, and then followed by the Pan-Topkins algorithm. Rest in week 11, I saw that most of them are just threshold-based detection, doing some filtering and all. So those kind of thing mostly you would be aware of. Now, if you have any questions from those, you can ask, and you can go through them in the coming up, it's like next Tuesday session. So apart from that, just one leaf left, and then you have your exams. So I hope so it would go nicely and smoothly. And we'll start with today's session then. So just to introduce myself, I'm Jagriti. I'm doing PhD at IIT Gandhinagar. I'm a second year PhD student, and I'm working in quantitative ultrasound for tissue characterization. So I have as some of you requested that if we can have an extra session or just a session with some more questions or something that has been asked previously, so that you guys can have a better understanding or idea that how it's being done. I have asked the people, but then it's a thing that I myself will also be giving the exam, so they haven't told me those things. So Professor Sudipta has a session tomorrow, or I guess day after tomorrow. So he'll be just like telling you the same in that one, and probably the Q&A or the question answers that are there in his live sessions would be the ones mostly correlated with the ones that you'll have in your exam. So it's like focus on those questions as well if some of you are just planning to it's like rely on assignments or having just some technical idea and then going. So we can focus on those quick Q&As. I've asked them for more previous to previous year questions, since this course is only offered once sem. So probably next sem it won't be offered. So we might have question and answers from the previous to previous sems, but I'm not so sure if they are same one as the ones that they're planning to give towards the next semester, or they do some alternate thing. So that I'm not so sure. So whenever they let me know, I'll let you guys know, or I'll keep you updated on that. So I guess that's it from my end, and we'll go with it's like today's one. If any of you have any doubts on the assignments or the questions so far discussed, or say you have your assignment due tomorrow, you can let me know. So we have this Wiener filter implementation. I hope the screen is visible here. So I hope that you all remember that how we did the Vena filter implementation and what it was exactly. So it's nothing but an optimal filter, and what it does is that it takes the ratio of the power spectral densities of a signal and noise. Now, when we implemented it, there was a lot of maths in it, but now here it isn't. So why so? Because when we did it, it was in time domain. Now here it's in the frequency domain. So we have everything optimized. It's Fourier transform, so we can directly take the ratio. So it's essentially the ratio of your desired signal the and nothing but your noise. So here it's nothing but the ratio of your noise to desired signal, or it can be as the desired signal divided by the total. So what in total you have is nothing but the signal plus noise. So it can also be written as SNR if you write it in this way, or it is also is like something as similar to transfer function, where you have your output first and then your input what was given to the system. Okay, so in this tutorial, it was asked that if create a piecewise linear model of a desired version of the signal that you want by concatenating all the linear segments. So that is P, Q, R, S, and T waves with its own amplitude duration interval that is similar to those in a given ECG noisy signal. So one data set of ECG noisy signal is given to us. So that's nothing but ECG LFN or ECG HFN dot DATs. So if you're finding any difficulty finding those, you can find those in the Q&A section. There, the online TA, he has uploaded all the tutorials, basic codes at how to plot them. But most of the codes are available there in the slide, so you can just have a look at them. So instead, it's like if you don't want to download them, but for data sake, you need to download those from there. But if it's fine for you and you just understand how the concept is going along, then you can apply it to any such kind of data. But just for hands-on, you can just try and download it. It won't take much of your memory space. Okay, so then they have asked us to find the PST of the model signal, followed by is like we need to see that what's the activity of the isoelectric segments for an idea about the noise. So if it's like you might have an idea that what the isoelectric segment were, the ones that we do not have any activity going on through, and can give us an instinct idea about how the noise is fluctuating, because there we do not have any physiological process going on. Okay, so that is how we define the isoelectric segment. Then we need to compute the PSD and the average, and then select the noise segment. So whenever we have a noise, we always say that this noise is with a zero mean and its variance is varying. So what does that mean is that noise is actually a random process that will have something that's fluctuating or varying over time, and it's not constant, not periodic. You're not able to classify it well. But then when we say that it's zero mean, then we say that okay, we can differentiate it, but it's just something that's very noisy or something that's very fluctuating. So we always say that if the mean of the signal doesn't have any idea about the physiology or the nature of your data, then it directly goes straight through and subtract the mean from your data itself. So will give you more and better understanding. Also, your signal would be, as like the baseline would be normal straight baseline with respect to the reference line, and there you won't have any fluctuation, or it won't be like hazardous for that process. Next is the last step is to implement the Wiener filter, but then you can just try and compare its output with synchronized averaging and then the low pass filtering. So you, it's like, can it's like I see that two students have joined today. So can one of you tell me that what was the difference in between synchronized averaging and low pass filter, or both of them are essentially the same thing, where we just get the smoothness and but high frequency noise isn't removed quite nicely? Anyone? Uh, I'll go ahead then. So for synchronized averaging, what we essentially do is that we'll take windows and then we average it through segments. Or we see that, okay, if I have some signal, and then I'll try to sync my signal with it's like the instrument that I'm taking my readings with, and I'll average it. It's like over the entire spectrum. So that's nothing but, if I say I have a transducer through which I'm taking my reading. So what a transducer is nothing but that converts from one form of energy to next, right? So I have a transducer and I'm sending the pulses to the transducer via pulsar receiver. Okay, so that has some crystal or source that's producing those segments or power or whatever it needs for the transducer to be active. So then since it's sending those pulses, so next thing, I want my this transducer as well as the pulsar who's sending the signals to be synced to each other, so that whenever the crystal is sending something as well as the transducer is sending something, both should be triggered at the same time. As and when they are triggered at the same time, will be that particular instant at when you'll be able to characterize your transducer, or how much energy or where it's focusing or what its dimensions or the physical properties are. You'll be able to like quantify all of them. So essentially, synchronized averaging varies from low pass filter like this. Whereas low pass filter is nothing but you take a cutoff frequency and then you take all the frequencies next to it. Okay, so that's how low pass filter is, like when you eliminate essentially the low frequencies and then take the higher ones. Okay, so let's try to implement it. So we know that Wiener filter is kind of a statistical approach to reduce the noise in signal. It also minimizes the mean square error in between the estimated random process and the desired process. So, but here what's our assumption? The assumption is that the signal and the noise, both of them are weak and stationary, saying that the characteristics are stable. But when it's applied to a non-stationary signals, it's not suitable for them because it's always fluctuating random over there. But there again, for non-stationary signal, we saw that that when we were learning about non-stationary signals and analyze them and process them, so we saw that okay, we can it's like differentiate or take two parties of this non-stationary signal as quasi-stationary and quasi-periodic, or say, and then process them. So that was how we were processing the non-stationary signals as well. So when taking the PSD of the signal, and then it's essentially take the PSD of the desired signal and the noise signal. Okay, so we'll start coding it. So then we had our data. So the input signal is there with the high frequency noise. We have the data loaded. We have the sample. So last class I showed how the noise is like ECG data was looking like. I haven't had pictures over here. I just wrote the code for your sake. But if you want to see, I can. This. So this is how the sample data was looking like. Okay. So this is very high frequency noise you have in here. So this and very again it's varying randomly. You can see that it's not average. You have multiple ECG going on over each other. Okay. So first what we do is like load it and then find the length of the signal. So always whenever you do signal processing, be is like valid through or be sure enough that you know what the data length of your data, what is your data length. Then at what frequency are you sampling your data? Is the sampling enough so that you're not causing an aliasing? What aliasing will do essentially will lead to loss of your data, and then you won't be able to differentiate in between two specific points. Then say if your point of application is something that you want to differentiate in between two sources or to quantify the resolution of a particular active source or a passive source, then in that case you'll need to know this characteristic of sampling aliasing very nicely, so that you'll be able to see that how well you are able to differentiate those 2 points, essentially characterizing the resolution of the system. Okay. Then from the length of the signal you'll be able to compute the time as like till what's the duration the signal is going through. And since we always deal it's in positive time domain and not with negative, but we know that frequency also exists negatively, because when we take Fourier transform it's always symmetric. So we do it positively and we take it twice of it, so that it's always as like we only have from 0 to n, because negative frequency negative time doesn't make any such realization. It's like saying that, okay, the famous example from H.C. Verma, that we threw a ball from the top of the building and then that the ball bounced and bounced. So whenever we started at t equals to 0, or at some point that we know that the at t equals to t when it was thrown. It's not always like, okay, when it went to its rest position that was t equals to 0, and when it started was something in the past. So it doesn't follow as anti-causal activity in here, it's always causal activities. Okay. So then we plot the signal. That's it for the plotting. So we know that, okay, how to plot it, find the sampling frequency, take the length, and then find the time domain. Time taking the time axis essentially dividing by the sampling, so that you know the instance at which two consecutive samples are occurring, so that you'll be able to plot the time for the same. Okay. Then we know that the signal that we saw just now, the input ECG signal, was highly corrupted with noise. Again, the T wave and P wave had huge amount of noise. So for the same, we need to design a Wiener filter to clean it. So what we do is that we take one cycle, is like essentially one duration of that ECG by linear approximation. By linear approximation here, I mean that I'm not taking any such segment that I think that is something very is like obnoxious or something very kind of tricky to handle with. So I'm taking something where I can play safe and I know that what's going on in there. Okay. So then what the is like the people have done, or how the instructor has done, is that he has taken the first 700 samples, and then there's a function called as g input in MATLAB. So what you do in from g input in MATLAB is that you essentially it's like whenever you write say x comma y is equals to, okay, I'll show you how the syntax of g input it. So you write it something like this: g input of your say this data or something that you're playing a role with, or you can just say like this: g input. Don't add a semicolon here because it will stop the process from being going on. So just let it be, and then say you're trying to add something a comma b or is equals to g input of something else. Now here you can always mention that how many points that you want. So if I want 2 points, it will give me 2 points. Even if I'm placing my cursor at one point and taking it once, it might happen that sometimes you take it twice, or sometimes there's a minute difference in between the positions. So just to be safe, I always do two whenever I'm doing something, but you can always take one also. It's just safer to have more than one something. Okay. So here is way, so when I have an image or something like a graph or so, so when I input this, whenever my code will come to this particular point to evaluate this line, what it does is that in that graph it will give me point and axis to select a point. So as in when I select the point in the command window, you'll be able to see that what is the actual value of x and y. If you add a semicolon in here, it's fine, it will run in its way and the variables will be stored in workspace. But then when you're doing something like g input, when you're doing something as activities that are involved in the graphical user interface, you always want that you should know how it's coming out along. You won't do use like you actually don't want to go into the workspace and find for those points and how the point is like what were the locations for the same, right? So x here is will denote the time axis, whereas y will denote the amplitude of your data. Okay. Similarly like this also. So I'll remove this from here. So Okay, so we took the ECG segment as the first 700 samples. Then while doing the G input, what they have done is that they found these two vectors. Okay, so first one was for the sample number. Say I varied it from 0 to 700 with the multiples of 50. So after each 50 interval, my time axis would be like 0, 50, 100, 150 like that till 700. And for amplitudes would nothing but the amplitudes corresponding to this values. Okay, so from G input they did like that, and they wrote those values manually. What you can actually do is that for the G input, you can, along with G input, you can give this vector and then store your values in it. It's like make an array, update, iterate it from I equals to 1 to say the number of times you're doing this G input, and then you save it along it. So you directly have your sample X with you, and you don't no longer have to, it's like write it manually and take a point. Okay, this point was this, now this point is this. Okay, so now when we do so, what G input gives us, or when we plotted the signal was also all our amplitudes were scaled in between 0 to 1. That is nothing but they were all normalized. So normally how we do normalization is divide, is like if I have a signal, I divide it by its maximum amount. So that is how I normalize the two signals. But if I have a signal, in order to normalize, how we also do is that first take the mean out of the signal. That is, if it doesn't have any idea about the mean and you don't know if the mean is carrying something, just subtract the mean from the signal. Now you have a baseline signal, a reference signal. It's like nothing but a reference in a way that it is symmetric along the x-axis over here. Not symmetric, but it's 0 is starting from the x-axis, it's entering till the x-axis. There's no baseline wandering in there. Okay, so in that way, how you compute this normalization is you take the signal minus the minimum of the signal divided by the maximum of the signal minus minimum of the signal. So that is also how you compute the normalization. So mostly people do directly divided by the maximum value, but you can also consider is like converting the signal into, so if you have a float signal or double signal, convert into uint 8. So that's nothing but 2 raised to 8, that's 256. So in that way it will help you to plot the signal efficiently, but it's not more of a followed technique, it was more of conventional. So nowadays people directly do divide by maximum. So or you can also, in MATLAB there's a command called as mat to gray. So what this does is that when you have all your value, it will scale them within 0 to 1. So it also essentially divides by the maximum values. Okay, so that was all for the normalization part. So then, so when we normalized it, now we no longer know that what our output signal is with respect to the input signal. So we scale it to make the same as that of the input signal. So we take the signal, take the maximum of it, and then multiply with the y vector that we had initially. Okay, till here everything's clear. Is that how we did it? So we plotted the data, curated it. So okay, we'll take one particular segment now, and then we are doing everything within that one particular segment. It's clear till here? Or if you want, I can give you some time to digest it. Mm. I'll wait for 1 minute and then we'll go to the next part. Okay. I hope the entire thing is visible. Mm. Okay. So next what we do is that what we had in a question is that create a piecewise linear filter version of the signal by concatenating the linear segments to provide the P, Q, R, S, T waves with amplitude duration similar to those given in the noisy ECG signal. Okay. So here, what we do is that take the linear model as an array. So we all know that there will be some values within it. It's always nice to initialize that first. It's like before starting the loop. So then we start -1. So since it's from 1, it would be -1. If it had been from 0, it would be till the end. Okay. So then what we are trying to see is that if our both is like here, now we are creating a linear model for all the segments that we had, like the P wave, the QRS complex, and the T wave. So now we are trying to see if any two consecutive points are equal or not. If they are equal, then I directly assign the isoelectric line to them. If they are not equal, then I assign a slope to them, depending upon their values. Clear? So how I do so in code is that I take the two adjacent points with respect to the index I that I had, that y of I and then y of I plus 1. I see if they both are equal. If is equal, assigns sees that if y of I is equals to y of I plus 1. Okay, so it's a logical operation. And then a is equals to, so that what it does, if this condition becomes true, then what it will do is a is equals to y of I times 1 of this entire vector you have minus of x of I. So what this gives you an idea is nothing but the difference in between the x, the timestamp, and we are essentially multiplying y of I with it, so it will add a straight isoelectric segment over there. Okay, so then if it's not the equal, if both two amplitude of in the y axis are not equal, so then what you do is that you take the initial value till the last value that you had, and you iterate is like make a line along with it by using the slope is nothing but y2 minus y1 by x2 minus x1. Clear? So this is nothing but it will give us a non-zero slope. Now assume that you have something 0 in here, and then this value is something very negligible with respect to this value, so it will overshoot it. So that's the case. You need to consider that you are not it's like the values that you are comparing are not going above your boundary limits. So whenever you're doing something like this, you should always define your boundaries, and it's like fit it within the two values. Okay, and then we are just doing it for the entire segment, that a is equals to a times 1 to n minus 1. Clear? So this is how we created a linear model and we stored our values within it. So for the same, we'll compute the length, time length of the it. And so first step is nothing but to compute the length of it. Sorry, I didn't do. And then you do the time of it. So when you do the time of it, you plot the model. So a linear piecewise model. So if you see here, normally ECG wave doesn't look like this, but here it does because we have artificially created the data. It's like synthetic ECG wave. So I created it, made these two lines, an isoelectric segment, the peaks, and this. So a very beautiful wave we have created here. Now next what we need to do is that we need to compute the power spectral density of the desired signal. Now till here everything was in time domain. Now we need to create a power spectral density. Power spectral density is essentially the FFT ka square. Okay, so for that you need to know that how many points you require in your FFT signal. Okay, so essentially if you say that everything your data points in are following along here in date, so it would be nothing but 2 raised to 8, that's 256. So you have 2 raised to 56, then we always want that whatever is there in your data should now say that we took this first 700 points, right? Here the segment was from 1 to 700, so the number of points that we have want to have in your ECG signal should be greater than those 700. So what we do is that 2 raised to next power 2 and then take the length of the signal. So the next power of 2 raised to this would nothing but 1024, that's 2 raised to 10. Okay, and then you directly take the periodogram of it. So periodogram will give you a power spectral density. So here this is the power spectral density and this is the frequency against it. But you don't normally plot the periodogram as it is. So we always plot a power spectral density and the units of decibels. So we take 10 log 10 of it. Now why not 20 log 10 is because this is a power, it's like entity. It's the voltage to the power 2. It's not essentially the voltage or amplitude where we'll do 20. So we take 10 log 10 and then we plot it. So here you can see it's essentially decreasing. So at high frequency, low frequency, it was higher, whereas it starts decreasing on the scale of order of around 40 decibel here when it reaches the high frequency, and then it saturates after a region. It doesn't become zero because power spectral density of a linear model will have some values till a particular point of frequency, till your say signal is being active, or there's some it's like signal is coming from an active source. As and when the source will stop, the signal will become zero. Okay, so the noise energy. So now we made our like piecewise linear model. We computed the periodogram of it, of the desired signal. Now we need to compute the periodogram of our noise signal. So what we do is that we take another template, and then what we do is that in that particular template we it's like the same process, we subtract the mean of the ECG signal, take the periodogram of it. So now for doing the noise energy signal, what is like taking just one segment won't suffice. So what you do want to do in that is that you need to take multiple segments in there. So I took that as like this, then the next cycle something like this, third cycle something like this. In the end, what I do is that take the average of all those three and plot it. So here if you see, it's not actually that varying with respect to how this was. So here it essentially shows you that you have something in your data, there's actual signal lying in there, but here it's just normal and straight. So shows you, okay, this is something as noise and it's fluctuating. If it hasn't been noise over there, it should have been a normal baseline or line at x-axis. Okay, so the PSD is more flat with respect to the that of the signal. So till here everything clear, because we just did it. Now the last step is just for implementing the Wiener filter. I'll just come in 2 minutes. I'll share the screen as well. Here we were till here, these 2 points. Okay, have a look if this is clear or not. Let me know. I'll just join in 2 minutes. Okay, so no doubts. It's like if you had, you would have spoken. It's fine then. So now we'll go towards the implementation of the Wiener filter. So just to give a brief, what we did just now is that we started. As like I'll just keeping going around through this because I believe that this is something important, the Wiener filter implementation and Pan-Topkins. Others are more like that of signal processing where you just need to know what you want to do. But here you actually should know how it's going along. So this is something will strengthen your core signal processing skills, and then following it, you'll be able to build up upon things. So you'll have a basic understanding when you're doing something as similar that this, so you'll be able to do it. So we loaded the signal, plotted it, and we took a particular segment, then scaled it because it was normalized. Then we created a it's like a linear model of the signal, taking if it was isoelectric, if it was equal, then we made isoelectric line. If it wasn't, then we made a slope along with it. Okay, and then we again plotted it. Next we had to find the desired signal ka PST. So how we do it is nothing but it's FFT squared. So we it's like for the number of points in your FFT, you took the max of it and then you formed the periodogram of it. Similarly for the noise signal, you took three different windows, and then for one window you do the same, second window you did, third window you did, and then at the end you average for all of them. Okay, uh, what happened? Yes. So now we have, what you have to do is that you have to implement the Wiener filter. So there is a transfer function of the Wiener filter that will be given to you. That is nothing but similar to this one. Is nothing but desired signal divided by the combined total of the desired signal as well as your noise signal. Okay. So here, um, So it's like define a particular array or function as nothing but zeros of 1 to length of f. So what is this f? F is nothing but the frequency of your parallelogram, because even now also you're working within the same range that you were working it's like from previously, that is nothing but 700 points only, and you took the frequency line or sorry axis corresponding to those 700 points only. Okay, so we're not taking the full length since it's zero after some certain point. So for now, we are just taking the first segment that we started off with. So from 1 to the segment line of it, what you do is that for the Wiener filter, you write what the transfer function of it was. That's nothing but 1 plus the ratio of noise divided by the desired spectra. So what was noise is nothing but we average it for three values. So that's nothing but pxx of average divided by that of the spectra is nothing but pxx of I. So it will here, now we knew, we have an idea of what this particular value is because we already pre-computed it. Now if you want to try and vary it, so it's like take different spectra and points, it's also possible from, but here I have just taken all those same things. And then for pass filter density for each particular point, it will vary from one frequency to one frequency, so you can't actually compute it beforehand, you'll have to compute it when you do it. Okay, and then since everything was in frequency domain, now we'll take it back to our time domain. Okay, so we take absolute of inverse Fourier transform of W, given say I'm giving it extra 200 points to this line, and then since I took the Fourier transform of it, now we have to convert it to time domain, so there occurred a phase shift. So that is nothing but from negative pi to positive pi. Since I'm using an IFFT shift, so what IFFT shift will do is like it will make it symmetric. We'll pad it with zero in a way that it becomes symmetric or centric around zero. So it starts from zero this side and then zero from this side. Okay. So filter the output in time domain. So then essentially in the end, what you'll do is that you'll convert this particular signal that you have after the Wiener filter implementation to the original signal that you had. This one. So you convert both of them. So here what you're able to see is that if you see here very nicely, it's visible that much of the noise that you had, the differences that you had, the double peaks that you had are now eliminated. More of baseline bonding also you don't have, so you can actually see how your signal is looking like, not unlike like this one where you had multiple lines and there's a lot of noise occurring over there. So then we try and compare it with the Butterworth filter, then synchronized averaging, Wiener filter. So we have already implemented the Butterworth filter, we have implemented the synchronized averaging. So what we see is that in Butterworth filter there's a smoother one, noise has been reduced, but Wiener filter, when we compare the Wiener with Butterworth, it has more noise to the though the bit more detail, but noise has been left behind. But when we do for synchronized averaging, now we all know that averaging is also more often a type of the low pass filter. So we see that it's better than the rest. It doesn't has any noise, it eliminates all the noise, but the high frequency noise nature, its biomarkers or its signatures are also present there. So everything has its pros and cons. So but if you compare the Butterworth versus Wiener, it has these points, and synchronized versus Wiener, it also has these points. So what did we observe is that Wiener filter is able to suppress the noise, but it's not completely able to remove them. And the output of the synchronized averaging is smoother than the Wiener filter. Output of the low pass filter is smoother but slightly distorted compared to the Wiener filter. Till this point it's clear. So we all just completed one big point, that was nothing but Wiener filter implementation comparison. How do you plot it, how do you filter it, how do you compute it's like define or write this Fourier transform, and then when you multiply both of them. So always remember that when you're working with filters and everything, you just don't multiply both of them assuming that okay, but here you essentially do convolution. Now why convolution? Because it also takes in hand of the previous points to the coming points, and then in a way it's like there's a quite good job so that you can convolve in between these two lines and improve the SNR or the signal quality. Okay, so if you have any questions, let me know. I'll stop for 5 minutes now. From 6:50 we'll start implementing the Pan-Topkins algorithm, and then we'll do the Q&A for previous year question. Okay. Okay, so if no further doubts, then we'll continue with the next one. That is to implement the Pan-Tompkins algorithm. Okay, so what we did previously, we are using the same data set here. So we'll just load the data, and then this is how the Pan-Tompkins algorithm is. So what we do is that we have an input ACG signal, then we band pass it. So what a band pass filter is nothing but a combination of both a low pass filter and a high pass filter. So always to implement a band pass filter, it's essential you take a low pass filter first and then the a high pass filter. You can take reversely, but then what will happen is that low pass filter always has some high frequencies with it, and then when you apply a high pass filter to it, it will take care of the high frequency component. So in a way, everything is being compensated. If you reverse the order, the low frequencies will be the one there within your signal, so that doesn't cause a problem, but high frequencies won't be eliminated that nicely. So that is where you face an issue when you change the order of this bandpass filter. Okay, next is the differentiator. So essentially to accentuate the QRS complex, that's a high frequency component you have. Then a squaring operation. So what you do is that take absolute everything. So by taking a squaring operation, you have everything as positive, as you do normally see in our rectifying circuits. That is when we have a half wave rectifier, full wave rectifier. So we have normal waves and we have a full wave rectifier. So that is how. So doing that point will help us differentiate in between the lowest amplitude signal to the highest amplitude signal. So the difference in between them would be exceeded, so that you'll be able to see very nicely and clearly that which particular wave is that, and how well you're able to differentiate in between the two ratios. Okay, after that you're doing a moving window integration. So if you'll be doing this in time domain, moving window integration is essentially the sum of all discrete points. Okay, and then you're doing some thresholding so that you can idealize or individualize all the points, that is say P, Q, R, S, S, T, U, V, like that, so that now you have a basic understanding that what the amplitude of the signal would be or how it would be along. So about that particular amplitude, this wave is this. About that this particular amplitude, this wave is like this. It's not that essentially that necessary that you always keep in mind the ideal values, but just if you see a signal, you see okay, this point is something higher than this, you know, now you might have known that what the trends are, how PQRS complex is. So from there you can do the thresholding parts, or else you can take some standard values that people have normally used. Okay, and then what you do is that you localize the R peak. So it's like localizing this R peak and then computing its location. So it's not that hard, because R wave is nothing but the ones that is say QRX complex, that's the highest in amplitude. So you'll be easily able to get through it and you'll be able to know it. So you directly localize it, take the point, starting point and ending point of it, and then give it to the spectrum. So from there you can compute different properties, say heart rate, how the pulse rate is varying, all those things you can compute from there. Okay, because you have your frequency with you, you have the time domain data, yeah, and you have the amplitude data as well. So from there, so from here everything is nothing but converting one domain to another domain. So you started off from time domain, converted to frequency, then into time. So it's not a role with the amplitude of the data, but you're actually playing with the x-axis. So you're seeing how the data, because this all signals, physiological signals, are time varying signals. So you need to know that what is the activity at this instant of time followed by the activity of the next instant. Okay, so I hope the algorithm was clear to you. Okay. So then why bandpass filter? I said that to avoid the low frequency artifact like baseline wandering, also to eliminate the high frequency noise. So it can be written as sum of this. Now for doing so, we need to implement both the high pass filter and low pass filter, because as such you don't have a function for a band pass filter. I doubt if there is in my Python, but it's not there in MATLAB. I say, as far as I know. Okay, so then you give a coefficient, say for B coefficient and then the A coefficient. So the numerator coefficient for your transfer function, the denominator one. So there's again a new function over here that's called it's dfill df2. That's nothing but direct form 2 digital filter. So this low pass filter, high pass filter, whenever you implement them, are essentially digital filters. They are no longer the analog filters that you normally implement or do it on your breadboard circuits. So I like when I was in my second, third year, I have implemented all these techniques and circuits and breadboard, and then later saw its output in oscilloscope. I hope so. You might have also done those things. So we define the filter in a way, and then you filter it out from the signal that you had. So now my signal has been filtered, so the low frequency component no longer has any low frequency components. I subtracted the mean out of it, and then I normalized my signal. Next, I have to do the high pass filter. So we'll do the same process: add it, filter it, normalize it, and that's it. Okay, so now what you have is nothing but your signal that was band pass filtered, so like this. So this was your initial ECG signal. Now you might say that, oh, the initial one looks more cleaner with respect to the one that is there in the signal after filtering with the band pass filter. So why so? Because here your sampling rate, you'll be able to see that, wow, very nicely how the variations are occurring, and then in between them you're able to see here the differences. So it might be due to the noise, it might be due to something else, but now since here the baseline was wandering, here it's actually stable, so you can actually do some quantifications from it. So but the algorithm is not over yet. Let's try and keep up with the next step. So what the next step is nothing but a differentiator. So what happens in this Pan Topkins algorithm is that I'll tell you is that you need to know the filter coefficients. Okay, if you're implementing a high pass filter or a low pass filter, you need to know the filter coefficients. Then next what you have to do is that create a digital filter, filter it out from your data. Similarly for differentiator, you need to know this. So if you have taken a course like digital image processing or biomedical image processing, we have the Sobel operators, we have, I forgot the name, but we have operator edge operators, and then canny edge detectors and all those things. So what we do in there is that we have a matrix playing a role with, or we have a square matrix or so. So a box average matrix and all. I'm remembering the names now. So okay, so what we have is nothing but we have the coefficients. So we have some coefficients along the diagonals, along the edges, along the corners, along the horizontal lines, like that. And then just by varying the coefficients of those filters, we are able to filter our data out. So the same way here also we are playing a role is that now you are changing the coefficients of your transfer function polynomials, and then you're taking the filter out of it. So it's not a new thing, it's just that you need to know the filter coefficients for A and B. Okay, so after doing so, what you see is that now you have gotten rid of this multiple peaks in here, because initially it was a confounding that, okay, this higher like more longer peaks can be my PQRX is like that QRS complex, but what if is this the smaller one? So now when we do this derivation for operator, derivative filter, because it accentuates that QRX complex, so now what you have left is nothing but this one. Because doing any sort of level of filtering, you're not able to get rid of the component. That means that it is something essential part of your signal. So here we can directly now say that, okay, this is my QRS complex that I have over here. Then I do squaring operation, that is nothing but ECG dot square. So there's again a function called as power. You can use that also, but what this will do is that it will is like if you have a vector say 1 2 3 4, and you have said that, okay, vector dot product and x is like this cap times 2. So what it will do is that it will give you squares, so 1 4 9 and 16. So square of each and individual elements are the data points, and then you normalize it. So what you get is essentially everything is positive half cycle. So what was also negative now became positive. Okay, so now we are able to see the difference in between the positive and the negative peaks, and then the positive and the negative peaks. So after that, what is the next step? So now you no longer have a role of sign in your data. So the next step would be taking the average of it, the integration of it. So what you do is that pad the signal both ways by the number of points that you are doing, then scale the signal with respect to the length of signal, that how we saw, if it's in 0 to 1, now you have to scale it accordingly with respect to the maximum value of the input signal. And then integration is essentially the summation in the script domain. Okay, that I said already. So this is how you're able to see your signal got more smooth. It has more of a single post structure, you can see. But now it's not looking like an ECG wave, because here also it was more of looking like a ECG wave, but now it's not at all looking like ECG wave. So what you should do, you should take the negative part now, and not a negative part, but yeah, something very symmetric to a normal ideal ECG signal, and then you see. So this is actually starting from a P wave, QRX complex, SU wave, as a TU wave, like that. Okay, so then what you do is that you take thresholding. Okay, find the location of the peak, detect the QRS points is like from one point to next point. So what happens from when you try to compute this QRX points is simply just that, okay, now you know that Q is something from where it started, the maximum value started. R is something from where the maximum value started and then where it ended, that is from became the starting point of S. Now R, then you know that when the R complex ends, so this is the starting point of your S, and then at some after some points you'll have the ending point of S. If that's clear, so how do we do that? Is nothing but for first location for the R, we take the maximum of both of them and then take the location in a way that's subtracting and adding an offset to it, but just to keep ensure that we have enough points lying here and there and we are not doing any hard first rules. Then for q wave we take the minimum of it, because we know that from here it's gonna start and then after some point it will soon dissolve. For s wave also the same, and then finally we find the s log is nothing but r plus s minus 1. So here s was sorry, so here s was nothing but the starting point. Okay, so then what we do is that we'll localize the peak that we have, we'll plot it, calculate the duration, the heart rate. Now here high frequency artifacts will still behave as like an artifact, because here it's no longer you're just removing your low frequency noise, but you are not actually getting rid of this high frequency noise. So sometimes they might occur due to the power noise or supply noise say effects, but then other points it doesn't and it will still behave like an artifact. So, do you have any questions within these two algorithms that we saw today? If not, then we can go to the previous year questions. If yes, you can let me know. If you don't want to discuss now, you can stay back and you can also let me know. That also works. So, if you want, I can wait for 2-3 minutes and then we'll go to the previous year questions. Okay. So, previous year questions are more of theoretical this time. So, without MATLAB, you'll be able to do it. The last 2 weeks, I also agree that it was more of MATLAB. So, that's why mostly that is like thinking and then how the exams would be, those points come in mind. So by the way, happy Gudi Vara to all of you. Happy New Year. Okay, if you have any questions, let me know and then we'll go to the previous year questions. So I think so. You don't have any questions now. So for the Q&A also we'll do that. We'll wait for 2 minutes. If no one answers, I'll show you the answer. So we'll go to the Q&A then. Okay. Zooming it out. I'll share this notes over here if you want to do. It's my same MATLAB code, but then someone's working on my workstation, so I was not able to show you exact implementation in MATLAB. If you want, I can show you it in the coming live session. If not, I guess if you directly copy paste these things, you'll be able to implement it. Just the case is that you need to import the data from your, it's like download the data from that Q&A section, and then you can follow the code along with it. Okay. So we'll go for the Q&A session. Wait. Should presenter view. My slides are not visible. Okay, perhaps I've only shared that screen. Mm-hmm. Yeah. Is it visible?
Yes, ma'am.
Okay. Is the first question visible? I guess not.
Not now, ma'am.
It's also happening. It's visible now.
Visible now.
Okay. I have to give up with all my answers then. Okay, let's do one thing. It's visible like this. It's not going into slide presentation mode. Um, share the entire screen. Presentation mode. Present it. Present view. Oh, I don't want you guys to see that. Okay, let's just stick with this one. It's fine. So in the Pan-Tompkins method, the high-pass filter calls the delay off. So if you remember, we did in this
B.
and B. Answers written down there. That's why. Oh, you know the answer.
No, ma'am, it's written in the observation.
It's written in the observation. Okay, cool. So, okay. Then how will you detect the S1 and S2 segments in the PCG wave? The lub-dubs. So one such method can be, you can use the same thing that we did now by using this Pan-Tompkins algorithm on the PCG signal, but then you don't really have those clear distinctions in the PCG signal, because when you have this dichrotic notch, everything becomes more fuzzy. So you don't really know that when the systolic and diastolic activities are going to come. So that's why people prefer that they extrapolate the location informations of the QRS complexes in the ECG signal, and then the dichrotic notch location, and from there you compute it, because essentially what you have in your PCG signal is nothing but the S1, S2, S3 and S4, where S3 and S4 are not that prominent, but S1 and S2 are. Yes, it's clear, right?
Yes, ma'am.
Okay. Next is the dichrotic notch can be detected using same question again, but now it's for the different application. So
Is
probably
it
this,
C?
yeah, it's C, the linear Rangan algorithm. So we didn't actually did this algorithm because it was more of theoretical, but then you need to know that which algorithm is applied for which pulse, or say now this was for PCG, you need to know that what is the standard for ECG, that was Pan-Tompkins. Now next would be what is the standard for EMG, for EEG. If it's there in the slides, make sure that you know all those things. Okay, next, the derivative based operators may be applied to detect. So when you have a slope, you can detect it's like through the derivative based operators, you can do that.
C, both A and B.
Yeah, yes. Next, on an EMG signal, a half wave rectifier is applied, followed by a low pass filter. Then what happens? So first, remember what a half wave rectifier was, and then we are applying a low pass filter. So essentially removing the low frequencies and then taking it out for the higher
Is it
frequencies.
B?
So it's A. So it increases. So as your cutoff frequency is nothing but till it's like it's confined towards a low frequency ones to filter the low frequency components. Now your filter response is increasing at higher frequencies, and then you have a half wave filter, half wave rectifier. So it will have some values at certain frequencies, then you have some values at certain frequencies, but then it essentially the frequency or it's like number of peaks with respect to the frequencies will increase.
Uh, but if we see theoretically, what the half wave rectifier does, the negative component is totally vanished. And in the
Yeah,
full wave rectifier, the negative components become the positive.
positive.
So if we see by that logic, I think it decreases number of
So
peaks.
yeah, so the now the difference is that we are not actually comparing half wave with full wave. Next, the thing is that when we have half wave with respect to full wave, it will be double times increasing. So that it's like the way in which the peaks would be going through, it would be twice of that of the those when we are following the low pass filter by the hyper rectifier, a half wave or a full wave.
Okay.
Okay. Next question, we have an EMG signal. The I guess it's not visible. Okay. For an EMG signal, the turns count values obtained from bigger window size is dash compared to the turns count obtained from a smaller window size. So is it smoother, a coarser, will remain same on an octave.
A smoother.
Yeah, so do you have any logic and answer for that? Okay, you know that what happens when we have more data, but then anything else?
It's given in the observation part only, but yes, this is the right logic that if we have the more data, then it is quite easy for us
Nice to
to
support.
get a smoother response.
Yes, that's true. Next is how many turns are present in the signal. That's why by following the MATLAB code. So now it's something that, okay, you have a MATLAB code, you can implement it. But then you know that what a sine wave is. Now you see that with respect to the frequency of the sine wave, how many times the sine wave will have the turns. Similarly, how many times the cos wave will have a turn. So that is how here we do that. So if we try and plot it, it's something like this. So we see that how many times it's crossing the zero axis, that many points is that is crossing it. So it's essentially 5 or something. So sorry. Yeah. So oh, it's 10. Change in direction of the signal. The turns are present. Okay, it's not zero crossing, it's turns. So how many times the signal direction is changing or the slope is changing will correspond to the turns. Okay. Next is the probability last. Okay. So how many zero crossing again? So for zero crossing, we again try and plot it. So we see
And
that the signal is like this. Yeah.
uh, can we see the previous question, like how you determine the terms there?
So by the number of turns. So first this turn you had, then this turn you have, then this turn you have, this turn you have, this turn you have, this and this one. So if you count it, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this one 10.
Like we are going to take some thresholding or something reference value. Like if we are going to count that point 1 to point 2 as a turn, if we see in the x-axis part,
This one.
point 1 to
This
point
one.
2,
Hmm.
yes, this is turn or not?
Yeah, it is. So this is your first turn, then this is your second turn, then this is your third turn. So whenever you have a change in direction or the slope is changing, that is nothing but the number of turns you have in your signal.
Okay.
Okay. Similarly, if you have to compute for zero crossings, it's nothing but by how many times the signal is crossing your x-axis. So its crossing is like more of like this 1, 2, 3, this 4, and then 5. Probably this one also, but I don't know. It's 6 or 5. It's 6. That's it. Okay. Then this is like to compute the RMS value of the signal. So you know the formula for computing RMS, it's root mean square. So you take the square root and the signal square, and then you normalize it. That's it. So this is how the formula is if you don't know. So it's like square root of the sum square divided by the length of the signal that you have. So in that way you can compute it. So this is something that you can implement it in MATLAB, because you can't really, it's like you don't know what's the amplitude of the signal followed by it. So even if it's scaled in between 0 to 1 at each and every timestamp how it's plotting through, for that you need MATLAB. Last question is also similar, that the now signal has been changed. Initially it was a sum of cos and sine. Here it's like a square wave signal. So again you do the same, but for computing for square wave it's essentially easier. So you can also compute it using the area under the square, and you can compute, take the square root of it. So you'll also have an idea from it. If not, mostly in exam, if they expect you to do it hands on, then the signals would be more of easier, that whose area under the squares or all those properties, like that. That's it for today. Thanks. If you have any questions, let me know. That's it.
And is there any function, inbuilt function to count number of turns? Inbuilt.
Of turns, I don't think so. Yeah. Oh, what you can do is for in MATLAB, right?
Like for RMS, there is a uh, inbuilt function called RMS.
RMS.
If you put the signal in it, then it will give the RMS.
Mercy. Mhm.
Likewise,
Yeah. So for number of turns, I'm not really sure. Let's Google it. Because whenever I've done it like thresholding types. So So, but if it's like you have the signal and you have to compute, then you can directly measure it. Number of terms, function. I don't think so. Multiple inputs, outputs. No. Mm-hmm. Signal. Count cycles. How many number of cycles we have? Here it doesn't. Probably there isn't because it's just a manual thing. But here it's cycles. So if you find for cycles, number of terms would be is like twice of it. So one cycle has 2 turns, something like that. But then he has done using find peaks. So that's essentially the number of peaks. Oh, you can actually do this one. Yeah. So, but it's not then that an inbuilt function, but yeah, you can find peaks for all of these. So when you do find peaks, it will count all the major ones that you see above from the negative ones. It will find all of those. Then you it's like say as the peaks that are greater than 0, so it will give you 2 peaks, that's the positive peaks and the negative peaks. The number of negative peaks that you have would be twice the number of turns you have, and the number of positive peaks would be twice the turns you have. Sorry, half of the turns that you have. Got it?
Wait a minute, like first I will find the positive peaks and then negative peaks, you are saying.
Yeah.
But
Yeah. Yes.
if I do summation of the number of positive peaks and the negative peaks, then I
Mm-hmm.
eventually get the number of turns only, na? How
Yeah.
the
Yeah.
twice factor is coming?
Yes. So if you just take one, if this waveform is symmetric, then you'll get directly one. But if not, then you'll have to take. So initially, I was thinking that it's like two-way through, but it's just the same one. So it will be just one here and then one here. So one is like both addition of both of them. The same thing that you said. Yeah, I
Okay,
guess
ma'am.
that should work. Probably that should work. You can try
And
once.
what is the logic behind the ZCR
Zero crossing. So it's just that
ZCR counting?
yeah. So whenever it crosses the zero axis, you count it. So I guess for zero crossing, you have a function in MATLAB. What was that? For zero crossing, you do have a function in MATLAB. We'll try and search it. Zero crossing. We have a function in MATLAB for that. So that is what is it's something else. From the zero axis, there are no. Where is the function? Something else. Mm-hmm. With zero crossings. Simulink. I guess it's not more of something like this. Returns zero crossing. I guess you just count the number of times it's crossing the x-axis, or else probably don't do it in MATLAB. It's very hectic then. Yeah. If you do it manually, it's more easy then. I think so. Detect number of zero crossings. It's the same thing again. Probably there was one. I don't know. I remember there was one, but Stack Overflow.
Okay, ma'am, it's okay. I'll send a message. No problem.
Okay, it's fine. Doing manually, it is more of fine. Or here they have tried doing it as like something that's less than zero and take only the positive. Oh, it's the same one that we have. The same signal. Okay. So what they have done is that they are taking the index where it's lesser than 0. So that is nothing but the signal that's up below it. So from there you'll be able to know the locations of the points that are negative, essentially. So if you just add as like the initial values which started at negative points, so you'll be computed. But that's more of kind of hectic, instead just plotting a line at 0 and then seeing how many points crossed it.
Okay, ma'am.
Okay.
Thank you, ma'am.
Thanks for joining.
Ma'am,
Yeah.
there is a live session on the 10th April. That is
Mm-hmm.
the next day.
Yeah, tomorrow.
So, can you please tell the Sudipta sir, or if you have any contact, that
Mm-hmm.
they will tell us about how to score good in the exam.
Exam. I'll let him know. So
Like,
the the session is from.
like uh, session is tomorrow. I don't know the real the timing. Wait a minute.
So when is there?
It is in the announcement.
It's tomorrow. It's like, okay. Might have got an announcement.
Yes, it's 4 hours, 16 hours. That is 4 p.m.
Okay, tomorrow 4 p.m. No, okay. In the morning, I'll let him know. So he might adjust. Or you can. It's just a live YouTube session, right? So you
Like
can add.
they like uh, there are, you can see here there are some Google forms here. So
Mm-hmm.
many students like ask this question, that how to crack the exams like this quiz. So I just want that you highlight this question and Siddhartha sir answer that. Like
Okay, okay.
if you have that much reach to as a
Yeah, yeah.
team.
Sure. I'll let him know. Then it's up to him. I'll ask him, but I'll do that.
Okay.
Sure.
Thank you
Okay.
very
Thank
much,
you.
ma'am, for taking my
Thanks.
request.
Sure.